Good evening. My name is Jill Trainer. I'm Dean of the College of Natural Sciences and Mathematics here at Sacramento State. And I'm pleased to welcome you tonight to our talk, which is presented by the College of Natural Sciences and Mathematics and the Sacramento State Center for STEM Excellence. STEM stands for Science, Technology, Engineering, and Math. The center works with area schools, colleges, universities, and employers to create a seamless STEM pipeline for the scientific and technical workforce. This is the first presentation this year in our public lecture series on regenerative medicine. This academic year, Sacramento State will host 4 lectures by prominent stem cell scientists in the field of stem cell research. This lecture series is funded by the California Institute for Regenerative Medicine and supports our new master's program in stem cell research. Earlier this fall, we were very excited to welcome our second cohort of graduate students into this graduate program. Students in our first cohort are currently conducting research with our partners at the UC Davis Stem Cell Program. As part of disease teams, these students are working with scientists and physicians on cures and treatments for disorders such as neurodegenerative disease, spinal cord and brain injury, epilepsy, HIV, osteoporosis, blood disorders, and burns. We look forward to graduating our first class of stem cell research laboratory professionals in the spring of 2011. We are very fortunate this evening to be able to welcome our speaker, Dr. Martin Birchall, who comes to us from London, England, though I understand he's originally from Liverpool. Dr. Birchall is a throat surgeon and professor of laryngology at University College in London. His clinical specialty is voice and swallowing disorders, and he's one of 4 internationally renowned laryngologists at the Royal National Throat, Nose, and Ear Hospital and Ear Institute. In addition, he runs a research program applying stem cells and tissue engineering to the treatment of laryngeal disorders. As a result of this research, Dr. Birchall co-led the team which performed the world's first stem cell-based organ transplant in 2008. That same year, Dr. Birchall was named Morgan Stanley Daily Telegraph Briton of the Year and was elected as Fellow of the Academy of Medical Sciences in 2010. Please join me in welcoming Dr. Martin Birchall.
Thank you very much indeed. That's the nicest welcome I've ever had. Oh, it's really sweet. Oh, who's she talking about? That's Elsa. Yeah, so, well, thank you very much. It's lovely to be in California, particularly at this time of year. In Liverpool, it really is very miserable. Although it's a little grey outside at the moment. It's more like home. But, yeah, I'm from Liverpool. I have a very tenuous connection with the Beatles, though, in that my English teacher used to play with John Lennon when he was a kid. So, but that's okay. That's vicarious. I'm some link there. And also, I'm sorry that the title has changed to this talk. I've changed it around a little bit. Anybody who's come here hoping that I'm going to be telling you about a new cure for asthma is going to be sadly disappointed, because I am an ENT surgeon. However, I will be alluding to potential treatments right the way down the airway, right into the lungs. So there will be a little bit for everybody, I hope. I am also a clinician. I am not a scientist, so although I'm one of these 4 stem cell scientists that are going to talk to you. However, the best part of my job is interacting with stem cell scientists and trying to apply some of the magnificent work that they're doing for the benefits of my patients, and hopefully for the benefits of lots of other patients in other specialties too, by learning from what's happening to ours too. So I work in London, which is a very exciting place to live and to work, a very multicultural, very diverse city. And University College London is the biggest university in Britain, it's the biggest university in Europe, in fact, with 4,000 separate research groups in the sciences. So that presents, a challenge, but also a great opportunity to bring people together, to focus, to build teams, to deal with the problems that we face in medicine that aren't adequately addressed by present treatments. And this is the Royal National Throat, Nose and Ear Hospital where I work. It was built in 1834 and it feels like it. It's very, very old indeed. We are hoping to have a new hospital built in the next few years. Happily, the staff who are there are first rate, very modern. We have a lot of modern equipment and stuff. But the building is very tired. I mean, just to show as an example of just how old it is, this room here was once occupied by Karl Marx when he stayed in London. It's true, it was. And this is my office down here, so we could have exchanged thoughts on communism. But so having said that, despite the fact it's very old and held together by sellotape and bits of twine, we get through 70,000 outpatients a year and 7,000 operations amongst 20 surgeons. So we're working quite hard there. And this richness of numbers of patients enables us to do lots of clinical trials. Of course, the National Health Service is a free at the point of care service to anybody in a way that a lot of other health economies may not be able to do. Okay, so that's what we do. But here's one of my great heroes. This is Theodor Billroth, who in the University of Vienna in the 1800s started the first surgical training programs. And he basically based his entire life in the hospital. He never really left. It's said that he didn't really get on with his wife, and that may be why he did this. But anyway, he certainly spent a lot of time there. And he built research into the training of the surgeons around him as well. And this is integral to what he did. Highly innovative man. He invented a lot of the operations that were still being done up until, well, at the time that I was training. The standard operation for a stomach ulcer was the Billroth operation, and that was as late as the early 1990s. But he also designed the laryngectomy, which is the operation used for laryngeal cancer, where you remove the larynx. When I finished my training in Australia, in fact, did a fellowship there, and I spent a lot of time taking people's larynxes out for cancer, because it was the best treatment. It's curative, it gives very high cure rates. But it's a very brutal thing to do. And it's disappointing that we're still doing an operation invented by this brilliant man, albeit brilliant, 150 years ago. We're still doing it to this day. So at that point in my training, 15 years ago, I said, I'm going to just explore as much as I can over my career whether we can actually do better than that, whether we can replace a complex organ like the larynx in some way or other. And that's what I've been trying to do. During this talk, you'll see a blue star at the bottom here from time to time, and that's to warn you that there might be a picture coming up of an operation with some blood in it, or something like that. So I don't know whether any of you are squeamish or not, but I thought it'd be fair to warn you in advance. I don't know. You may even be looking forward to them. So we are. It's not really that bad. Okay. See, it wasn't that bad, was it? Okay. So we are still doing this operation today, and we have very good ways of rehabilitating people. We also do an awful lot of chemotherapy for patients with head and neck cancer. A lot of the big trials done in the United States have shown that the best cure rates can be gained by adding in chemotherapy to surgery and radiotherapy. And in fact, that by using chemotherapy and radiotherapy alone, you don't need to necessarily take the larynx out. You can actually retain the voice box and not take it out. This is what's called organ preservation surgery, and you can use similar techniques to preserve other organs in other parts of the body too. But preserving an organ is not the same thing as preserving its function. And the main outcome measure from this was preserving the presence of the organ. And in many people, it no longer worked properly, like in the example shown in the bottom right-hand corner of the slide here. This was a larynx, but it's been converted by chemoradiation to something that really doesn't function like one anymore. So my hope is that if we can actually lower the bar by which we can introduce surgical techniques with the very best help from bioscience imaginable, that we won't necessarily have to use these highly toxic agents. They give you about a 10% survival improvement, but about 3% of people actually die directly as a result of the chemotherapy. So if we could have functional surgery, I think we'd be doing our patients a big favour. So I had a dream. This is Carl Sandburg, who's one of your great American philosophers who wrote the standard biography of Abraham Lincoln, in fact. And I believe that's true. So that's my dream, that one day we can replace organs without the need for complex and disfiguring procedures or drugs. So what ways have we got of rehabilitating the voice box, this incredibly complex structure that I'm using to talk to you today? Well, we do have ways of doing it. After you take the voice box out, we have very good speech therapists who can restore some kind of voice, either by getting people to talk through a burp, which you can do, or by using electrolarynxes, which sound a bit like this, like an electronic larynx, or by using voice valves, which are plastic valves that go at the back of the windpipe and allow you to talk between breaths, a bit like this. So these are ways in which people can get their voice back, but it's not normal voice. We also greatly understand the process of swallowing now, so we can rehabilitate people swallowing a lot better than we used to be able to. And there are improvements in other forms of technology too, such as tubes and the way we look after the airway here, and these valves that we put at the back of the throat. So certainly we're very much better now than we were when I was training in Australia at getting people back into life again after taking their voice box out. But it's definitely not the be-all and the end-all. So this is what a patient's like after they've had their voice box out. So the voice box used to be here, and now it's gone. So here they have, it's not very bright this actually. So this bit here is the windpipe, and it's connecting straight out onto the surface of the skin. And that's what they're breathing with. Whereas here's the swallowing tube down the back here. And they're disconnected apart from a very small valve, just there. If I flash it on and off, it works actually. There you go. Just there. So, and a plastic valve, which does allow air to go up through the valve, and then by constricting the muscles at the back of the throat, you can generate sound and give some sort of speech. Not everybody can do that. To do that, you need to have good coordination, you need to be able to see properly, you need to have a good intellect, and also not develop problems with swallowing either. So we understand the process of swallowing a great deal better too. You need a functioning larynx to swallow in most cases, but you can actually get stuff back past this now. So we understand that you need an effective trigger mechanism, so the tongue has to propel backwards into the pharynx and then get the stuff down beyond there too. Swallowing and talking are absolutely fundamental human activities. So too, I've taken this from a... So you can get people back into some sort of side. Very few of these people actually go back to normal work, though. So when these people come back to see us for follow-up, they generally tend to look on the bright side of things. But we know that they don't go back to work, and very few of them adopt normal social lives again afterwards. So is the loss of a larynx so bad? Well, these are you probably hate these guys, don't you? Having put this, I've suddenly thought this is probably your enemy here. But anyway, these are Aggies. I put this up simply to point out that if the larynx fails in animals, it's not such a big deal, because the larynx in most animals sits up behind the nose. For very good reasons. It means that if they are exerting themselves, in the case of a racehorse, they can convert everything from the nose to the tips of the lungs into a linear tube. So there's air pumping through into a straight line. But because the larynx sits up behind the nose in most animals, if it goes wrong, they don't have problems swallowing. We have made a big exchange to become humans, in that our larynxes have descended into the neck, and this allows us to communicate verbally. But in doing so, the slightest problem here means that food, drink and saliva go down onto your chest. And that's a really big issue when the larynx goes wrong. So loss of a working larynx can cause pneumonia, dysphagia, really serious issues that you don't get in horses. Speech is fundamental. In the turn of the 19th century, 80% of people worked with their hands, and 20% used the power of speech as part of their working lives. The turn of the last century, it was the other way around. 80% of people now have to verbalise in order to function properly at work or in society. And only 20% of people rely primarily on manual labour. So if you strip voice away from somebody, in many cases you're stripping away their capacity for livelihood, in most cases, and certainly a full participation in society. This is an advert for the Napa Valley I found. So it's really cheesy, isn't it? It's just awful. But it crystallises some of the other relatively minor issues about not having larynx. If you haven't got a larynx, air is not coming up from your lungs and through your nose. So you can't smell properly and you can't taste. So no smell and taste. Also, you can't cough effectively, because in order to cough, what you're doing is you're using your larynx to trap air in your lungs. And that builds up pressure And then as soon as you open the vocal cords, it all comes out. Okay, you can do that. And similarly, you can trap air in your lungs in order to lift heavy weights or to strain, so if you're straining against something. So people without a larynx can't do those things either terribly effectively. And like this couple here, you can't even kiss properly because you need air. Anyway, you need air going through the mouth in order to kiss. You can try it at home later on. You don't have to do it now, but it doesn't really work. So you not only lose the power of speech and some ability to swallow, smell, taste, living, coughing, tasting, and kissing. And these are all fundamentally human things. They're things that really make us what we are. Yes, you can do without a lot of those things. These are not life-saving things. But they are fundamental to being human. And that's why I personally have gone on this one-man crusade to replace the larynx. So, how could you go about this thing? Because this is an immensely complex organ. It's supplied by more fine motor fibres than any other part of the body, more fine sensory fibres than any other part of the body, in order to do what it does. To allow you to breathe, which is very fundamental, but not aspirate all your food and drink. To protect the airway and allow you to breathe, and allow you to talk as well. It's a very complex mechanism. So how can we do that? Well, the first way we tend to rebuild the body is by moving around patients' own tissues. The simplest way of doing this is by a skin graft. So if you have a surface with area missing, you can put a skin graft onto it. More recently, we've developed the technique of free tissue transfer, which is where you can borrow a part of the body on its own blood supply and plumb it in somewhere else. And it's commonly used to reconstruct defects in the arms and legs. We use it a lot in the head and neck for patients who had their tongue removed, parts of the oral cavity. You can, for example, take the fibula, the thin bone along the side of the leg, with a covering of skin and its own blood supply. You can break the fibula into little sections and plate them together into the shape of a jaw and replace somebody's jaw. So free flaps have greatly improved rehabilitation of patients, but they're not sensate, they don't sense anything, and they don't move. They also don't look like the native tissue, and they can break down. There can be issues with them. Prosthetic materials don't really do the job. If you put prosthetic materials into an area which is dirty, like the throat is, full of bacteria, they don't really stay there. They can get infected, displaced. They're not terribly effective. You can do classical organ transplantation. You can move things around using immunosuppression, and I'll come back to that in a minute. Or you could use the fruits of the new revolution of regenerative medicine. Another slide. There you are. So close your eyes if you're squishy. Okay. Ooh. Free tissue transfer. So this is free tissue transfer. So here we're putting a free flap. This is actually a free jejunum. You can borrow parts of small bowel to rebuild the esophagus up here. You move a bit of small bowel into the neck, and that's what we're doing here, in fact. This is Jack Hawkins, who's one of our great British actors. He had a laryngectomy back in the 70s. He had a wonderful Shakespearean voice, and he was so desperate to get his voice back that he tried a completely unproven prosthetic device, which became infected, and he died as a result of that. And despite a lot of technological innovations since then, new biomaterials, advances in electrical engineering, we've really not been able to generate something that works as an electronic larynx. What about laryngeal transplantation? One has been done, and I'll come back to that in a minute, but there are a lot of issues with this. I think the biggest issue is that this is a transplant for quality of life and not for quantity of life. So here we're saying we're going to put you on immunosuppression and put you through a major operation for something that's not going to save your life. Immunosuppression, on average, reduces your lifespan by about 10 years. So this is a big thing to ask of somebody. But should we really impose our own values on that? Well, I'll come back to that in a minute. So the ethical framework is a question. And then what are the indications for doing this? How many people would actually be suitable to have this major procedure done? Can we get the nerves to work again? And then there's the question of immunosuppression, as I say. Plus, would it actually be cost effective? In a time when certainly our health system is stripping 20% of costs out of national patient care, and I know your systems are under pressure too, should we really be thinking about things like this? There was a laryngeal transplant performed in 1998 in Cleveland, Ohio. This was a guy who'd been a motorcyclist, and he was cycling along and hit a wire across the road. It was one of these gangland things, and damaged their neck. He was about 45 at the time he was considered for this, was otherwise fit and well, and he had an organ transplanted in. He subsequently retained a hole to breathe through in his neck on a permanent basis, because if you directly repair motor nerves to any part of the head and neck, they don't grow back and give you function. So if you repair the face, for example, the whole face moves together. If you repair the tongue, likewise the whole tongue will move together, and so too the larynx. You can repair them, and the muscles will have bulk, tone, and health, but they won't move in concert. So you need a tracheostomy so you can still breathe and protect the airway. But the sensory nerves grew back very well. He was able to swallow very well thereafter. And one muscle worked quite functionally, which allowed him to lengthen and shorten his vocal cords. And so after this operation, he had a very active career as a professional speaker, in fact, as a motivational speaker. 12 years out, his organ is still in place. He's showing some signs of chronic rejection now, but it's the first time that an organ's been transplanted and kind of worked first time. Now, he is on immunosuppression still, and he still has his tracheostomy. So a lot of my colleagues would say that this was a failure, but I think for a first off, it was pretty successful in that sense. And he swallows normally. He can eat and drink anything. This is the city of Medellin in Colombia. And in Medellin, Colombia, it is said that they have done something like 20 laryngeal transplants. We don't really know, but because they haven't published anything yet. But nonetheless, they've registered them on the International Organ Registry. And so we hope that they will actually tell us a little bit more about how successful this is or it isn't. We don't quite know what the ethical framework for that was either. So, okay. So what about the indications for doing this? What sorts of people would you do it for? Well, you certainly wouldn't want to do it for a cancer patient first up, because if you immunosuppress somebody with cancer or potentially still got some microdeposits of cancer around, you may reactivate it. So we certainly wouldn't want to do that first up. So the first sorts of candidates would be like the motorcycle guy, people who had trauma. So this patient here, for example, is a patient of mine who swallowed caustic soda as a child and basically has no airway through at all. So there's no way through there at all. So a completely non-functioning larynx. Or alternatively, somebody like this who has the opposite effect. This was an inhalation injury, a burn injury, and this person can't close their larynx. In a way, this is worse than that, because this person can swallow, and this person, every time they try and swallow, it goes down onto their lungs and gives them pneumonia. So both of these people have very serious issues, but they're relatively young. And so do you want to transplant somebody like that? The Royal College of Surgeons in England recently had a committee put together to decide whether it would be worthwhile putting people through organ transplantation for this. And you don't need to read all this. But in essence, the bottom line here is that they thought that it probably would be indicated under certain circumstances. There were two ethicists on this as well, and the professor of philosophy from Oxford was on it as well. And it raised a very interesting point, actually, that most clinicians would say, no, it's not worth it, because they're potentially going to lose 10 years of their life, and there are all these other complications of immunosuppression. And we do that a lot, particularly in surgery. We impose our values on what patients actually think themselves, and we assume there is the burden of ethics for them. But should we really do that in every case? Perhaps for some people, the exchange of those lives, that life potential, the risks of immunosuppression are worth it if you can swallow, talk normally, smell and taste your wine and food, that you can sniff and you can kiss your wife again. Perhaps that exchange is worth it for some people, and should we really be so judgmental as to prevent them from making that decision? So this was a very interesting outcome, and it may open the door to us doing laryngeal transplantation in the future. Okay, so I had done a lot of preclinical work, and so there are ethical issues around animal research, I appreciate, but there's this work and all the work I'm going to show you depended fundamentally on our ability to use appropriate large animal models in minimum numbers to achieve our aims. We could not have gone straight into man with a lot of what we did. So we used a pig model, and we actually were able to develop a lot of the concepts towards clinical laryngeal allografting, classical transplantation larynx, in the laboratory using our pig models very well. But you still need to get the nerves and muscles to work again properly. And how do you get them to work when, as I say, all we're achieving by repairing these nerves is that they persuade all the muscles to move at the same time because there's no selectivity. They don't have the pathfinding ability that you see in embryos. So one way of doing it is to borrow from Peter to pay Paul. So you can take a nerve that normally does one function and get it to do a different but related function. In this particular case, the phrenic nerve is the nerve that drives the diaphragm. When you take a deep breath, diaphragm moves down, phrenic nerve. That's exactly the same motion that we want to occur in the muscle that opens the larynx. So you can borrow some phrenic nerve fibers, put them onto the single muscle that opens the larynx. So every time you take a deep breath, not only does your diaphragm move down, but the larynx will open too. And this has been explored, but we've actually got much better than this over the years. And this is actually a method that I'm using in some of my patients at the moment. We could use neuroscience a lot better than we're using it too. There's a much greater understanding about neurotrophins of one sort or another and their potential therapeutic uses. But neurotrophins haven't quite made it into clinic yet. They've been almost there on a number of occasions, and then there have been some concerns about the development in neural tumours, usually benign, but maybe some others too. And some of these may indeed be carcinogenic as well. So we need to be extremely careful about this. Again, the appropriate minimal use of appropriate animal models or animal substitutes in the laboratory will allow us to screen these things rather better. So you can use more neuroscience. Alternatively, you could skip all that, say that's all too complicated, and just stick a pacemaker in there. Pacemakers like they're used for hearts. And if we had one that allowed the muscles to open and close at the right times, perhaps that's the way to go too. Here we use something called NT3, a neurotrophin, to see in our pigs whether we could get the nerves to grow back more effectively. In essence, what we saw at the 2-month mark here was that the ones with neurotrophin grew back a lot quicker and the fibres were denser. The green is the nerve fibres here, a lot denser than the ones above, the controls here, in these pigs. However, by the 4-month mark, there was no difference. So the neurotrophin was great at getting things to grow back quicker and in greater numbers, but when it got there, it did much the same sort of thing. It didn't do the pathfinding that we wanted it to do. So we weren't there with that. So you could explore other things like the ephrins and netrins and some other clever molecules which do the pathfinding for embryos. And that may be the way forward in the future. But we're clearly not there yet. So that. Oh, another star. Yeah. Okay, so this is not that scary, is it? So what about nerve stimulation? Nerve stimulation is something that's been explored for the larynx for about 10-15 years. And the problem here is that you need quite big voltages to stimulate muscles directly. And implanting electrodes in the neck is a difficult thing because, first of all, they corrode, and secondly, they move around a lot. The neck's a very mobile area. However, there have been some recent breakthroughs, again modelling on improved cardiac pacemaker technology. This is a group in Germany, in fact, who are doing this, where they've found that they can actually use the neuromuscular junction as the point of stimulation. So you need much lower voltages there than you do for directly stimulating muscle. You don't damage the nerves, and I think this shows great potential. This is actually one of the German researchers themselves stimulating themselves. So they've here got a needle electrode going from the front of the neck right the way through the back of the larynx, and into the muscle at the back, doing this critical opening motion. A paralysed larynx generally tends to lie with the vocal cords together, which is great for speech and airway protection, but doesn't allow you to breathe. So if you can just get it open, that might be all we need. And just to run that again, will it run again? Maybe it will. Yeah. It's a very quick video, isn't it? It's a very disappointing video. Go back. Go on, do it again. It's very quick. You blink and you miss it. There you go. Hey, how about that? So there we go. So this is somebody with a paralysed hemilarynx and stimulating, and it works. Again, it's early days. It needs packaging appropriately, and we need more evidence of efficacy. But it's getting there. Just as a side issue, one thing that we found while we were investigating transplantation of the larynx is that the larynx turns out to be a highly immunologically active organ. And without going into it in too much detail, it's a very sensible place to put an immunological checkpoint because everything you breathe, everything you swallow goes past the larynx. And so if you were going to design a place that was going to be sensing the environment and stimulating the immune system or downregulating the immune system appropriately, this would be a very good place to put it. And I actually think that's what it does, but I haven't proved it. It's a very difficult thing to prove. So highly immunologically active organ anyway. Okay, here's another quote about dreaming. This is Hitchhiker's Guide to the Galaxy. Anybody read this? Yeah. Yeah, I thought I knew you would. It's Mr. Monty Python down here. So, The Hitchhiker's Guide to the Galaxy. He was a dreamer, a thinker, a speculative philosopher, and this is what my wife thinks. She thinks she'd rather gone into private practice and earned $1 million taking out people's tonsils. But I think it would have driven me bonkers. So there we are. So I'm an idiot, according to my wife, but there we go. She's stuck with me, so there we are. All credit to her. Okay, so at this point in time, we'd reached a certain point in laryngeal transplantation. It was kind of feasible, we were getting some ethical support for it, maybe the nerve stimulation would work, but it was still some distance away from being a very, very practical alternative. The early part of the last decade, we started hearing about great things happening over here. This is Anthony Atala at Wake Forest University, and he, in about 2002, started doing tissue engineering for babies' bladders. These were babies born with a defect on the anterior wall of the bladder, and traditionally these were managed by urinary diversion, so they would never really be able to pee, basically. And what he did was, he built collagen scaffolds and put mature cells onto them, muscle cells on the outside, lining cells on the inside, and built bladders and put them into these babies. Now these are tiny babies, they're premature, so they're this size, so the bladder's very small. So it's a very small area. Nonetheless, it showed great promise. And 4 years down the line, they still seem to be working. The first few didn't work as well as the later ones, and that was a great lesson for everybody involved in this kind of science, actually, that it requires a different approach from the regulators and a different approach from those designing trials, because when you're starting out, you do have to incrementally improve things, make things a little bit better each time. You can't suddenly say, I'm going to do this for 10 patients. And that's an interesting thing for regulators to get their heads around. Nonetheless, he did that. It's now working very well for adults too, needless to say. And there have been lots of wonderful spin-off projects at Wake Forest. For example, the ureters, female genital organs, and some other stuff too that they're doing there, which is all very exciting. So here's one of the bladders that they built. We were very inspired by this and immediately started exploring the potential for this in the airways too. This is regenerative medicine, broadly speaking. I'm sure you've come across other definitions. This is a UK definition, of course. And so we're calling it here the use of cells and tissues to restore or replace function. And the main message here is that regenerative medicine is not one technology. It's a whole raft of things, many of which existed before regenerative medicine gained the popularity it has today. So cells, obviously. Stem cells also. Gene therapy. When I took my exam to get into medical school, and look at me, that was a long time ago, I had to write an essay on gene therapy back then. So it's been around a long time and is now starting to bear fruit, in fact. And biomaterials and nanotechnology, so all of these things, a wide range of disciplines. Certainly too much for one person to be an expert at. And a compelling argument for the building of disease teams like they're building here in Sacramento. Okay, so, stop. Thank you. So we had started to apply some similar technology to that used by Anthony Atala in our labs in Bristol and Spain. And we initially tried out replacing the trachea, the windpipe. This is a very logical place to start rather than the larynx because it doesn't need to move. It's a simple conduit. It's just about the simplest organ you could possibly think of building. It's just a tube, it just needs to get air through it, and it's got a set of lining cells on the outside and a set of supporting cells on the outside. So, relatively simple thing. And we'd done some experiments in pigs where we'd found that if you put in a scaffold on its own, it tended to collapse and get infected. If you put a scaffold with epithelium, it didn't get infected, but it still collapsed. If you put in one with cartilage cells on the outside, it had support, but got infected because it had no lining. But if you had scaffold and two types of cell, all the pigs survived. So that's the kind of point we were at. And then this unusual patient turned up. She was a 30-year-old mother from, again from Colombia as it happens, who had tuberculosis of the main airways in her early 20s. And this had led her to have seriously scarred airways on the left-hand side. She had multiple procedures which had only served to shorten the airways further and had pulled the trachea up against the aorta, the big blood vessel in the chest, which compressed it even further. And at the time that we came across her, she was getting more and more chest infections and heading rapidly downhill and spending all her time in hospital. The only conventional treatment for this is to do a pneumonectomy and remove most of the trachea as well. So take the lung out and most of the windpipe. It has a 50% mortality, that operation, and you never have any exercise tolerance afterwards. You can't really get upstairs and things. So not something to impose on a 30-year-old if you don't have to, it has to be said. So we put it to her that this was pretty untried technology, and put this also to the local ethics committee. She presented in Spain, in fact, and the national ethics committees in Spain. And the patient and both sets of ethics committees said that this would be a reasonable thing to do. And so we went ahead. This was 1998. Sorry, no, 2008, I beg your pardon. Back up. My apologies. Newfangled computers. There we are. So, slideshow again. We'll get that. Okay, good. Right, there we are. So, this is her. And so she had a problem down here. And this is what it looked like. This is a 3D reconstruction of the tight area, the stenotic area in her bronchus. And it was collapsing, and it was brought up against the aorta there. And so we took a cadaveric, so it's dead. It's got a little tag on its foot there, so it must be dead. And we took out this was an organ donor in Spain, so they have a very good organ donation program. It's an opt-out scheme, which we wish we had in the UK. We took the windpipe from this organ donor and stripped out the cells using a combination of detergents and enzymes, with a fairly crude protocol then, which we've since refined. We then took some of her stem cells from the bone marrow, and also some airway cells from her windpipe and from her nose. Both airway cells. We didn't know which type of airway cell would be better. And we grew them up. Stem cells expand readily, and you can then differentiate them later, as we did, into cartilage cells. We put the tissue into what's called a bioreactor, which is a box in which you can do various things, and seeded the cells on. We then tested the biomechanical rigidity of the structure, and it seemed fine. It seemed very similar to the native structure. We took it to theatre and resected the area concerned, which was windpipe and bronchus. So out that came. And in went the new bit. It was as simple as that. Actually, there are a few other bits of clockwork in the chest, actually, like hearts and stuff. But anyway, and it was incredibly serendipitous because we hadn't really tried this before. But you know, by chance, the decellularization left us with something which could be carved to shape and which did have the right biomechanical properties. By chance, she was just the right size and shape, and we had a donor of the right size and shape. And everybody was in the right place at the right time. Whenever you do something like this, serendipity plays a huge part, and there's no question in this case that that was the case. So, that was 2008. She did develop some tightening in the proximal, that's the upper end, a few months later, and had to have what's called a stent put in. A stent is a metal or plastic tube that holds open a hollow structure. But that only stayed in place for 6 months, and since it came out, she's had no further problems at all. She now works full-time, she looks after her 2 kids, and travels back and forth to Colombia to see her father. And she's right as rain. So, 2.5 years out, she's doing really, really well, and is a major success story, we believe. Okay, so, subsequently, we've done a further 5 adults, in fact, although with much shorter follow-up periods. In November of last year, I was phoned by my colleague at the Children's Hospital in London, which is called Great Ormond Street Hospital. He is an expert in paediatric airways, and he had a particular child who was born with a 1 millimetre windpipe. You normally need 4 millimetres to breathe through, so this is it's incompatible with life. So at birth, had the windpipe replaced with a cruder version of what we were using, some preserved cadaveric material, held open by a metal cage, a metal stent, and had a succession of these stents put in, which had managed to keep him alive for 11 years, which is very impressive, actually. Nonetheless, he hadn't had a terribly normal childhood, very limited exercise tolerance. But in November of last year, he had a sudden bleed. He suddenly had a huge bleed and coughed up a lot of blood at home. Was taken in, and the metal cage that had been holding open his windpipe had eroded into his aorta, the big blood vessel in the chest. So, a very knife-edge situation. He was transferred from Belfast, where he lived, down to Great Ormond Street. And Martin phoned me up, my colleague, and he said, you know, we really have no conventional solutions for this. Could we use what you used for the woman in Spain here? I said, well, I really don't know. You know, we haven't done that. In the meantime, we had been working on a speeded-up form of the protocol, however, And this was our first opportunity to use it, because there was no conventional treatment for this lad. We have ways of repairing the aorta, and in fact it was repaired using a combination of what's called Gore-Tex, which is a biomaterial, and a decellularized porcine graft over the top. So we have ways of doing that, but not the windpipe. So we said, well, we'll give it a go. And then it was a race against time at that point to see whether we could actually get an appropriate sized donor and decellularize it in time before he bled again. So this is what happened here. If I can get this one up. If I can. Okay. So as it happened, we were able to link up this time with the Italian authorities. My colleague Paolo Macchiarini had moved from Spain to Italy at this stage, and the Tuscan authorities allowed us free rein to retrieve tissues from traffic accident victims in Tuscany, in Italy. And a few weeks after we got the call, an ideal patient turned up, who was a very small woman, in fact. And we were able to put the trachea through a modified protocol, which was a lot quicker, and stripped out the cells a lot quicker. And we stored the organ. Then what we did was an intraoperative protocol. So instead of differentiating the cells outside the body, we took the child's own stem cells. Not only was this quicker, it gets around a ton of regulation. Provided you don't manipulate the cells in any way, you actually get around all that, and you can actually do it using fairly conventional ethical permissions. So again, he had this horrible trachea. In fact, we had to cut the metal cage out with metal cutters to get it out, in fact. It was so stuck in there. We also used some growth factors, and these were based on a similar cocktail which had been successfully used for a skin bandage, actually, in Germany. And there's some similar work going on here at the moment. We took his bone marrow cells, we separated them out in an adjacent laboratory, and we seeded them on intraoperatively onto this graft. And we took some strips of normal epithelium from the trachea we'd taken out. There wasn't a lot of it, to be honest, but we put some in anyway, and seeded the inside of the graft. And then injected some EPO and some TGF-beta, which allows the cells to differentiate into chondrocytes, we hope. The EPO allows recruitment and angiogenesis, that is the generation of new blood supply, to occur as well. And place this in situ in the child. And this was the longest section of windpipe ever replaced in anybody. It was 7 centimetres. The previous longest was 3.5 centimetres. And most people would say that we couldn't do this because we didn't revascularize it. When we're doing these free flaps, these jaws I was talking about earlier, they have their own blood supply, and you repair it at the time of surgery. Here, this has no blood supply. We're relying on the body to move in and provide blood supply as quickly as possible. We did augment it a bit, however, by taking what's called omentum, which is some fatty tissue from the tummy, and pulled it up. But nonetheless, we were relying on the kid, and maybe the EPO too. Okay, so what happened to the kid thereafter? Well, he has had some problems post-operatively, mainly because, in retrospect, we weren't brave enough. We didn't replace his bronchi, which are also diseased and also held open by metal tubes. And those are what's now limiting him. He's able to breathe much better than he's ever been able to breathe before. He has a wonderful windpipe. And he's actually growing faster than he's ever grown before. Okay, boys do grow at the age of 11. It may be coincidental, but he's put on 2-3 centimetres just since this operation in March. And he's now back home in Belfast, and he's started to go back to school in September. So, again, a major breakthrough in that sense. But he does have to keep coming back to be checked because of these stents down here. Also, it took a very long time for the epithelial lining to grow back again. And I think this is an area that we need an awful lot of work in the future. There's a better understanding of epithelium. The understanding of epithelial stem cells is a particularly difficult area of stem cell biology. Identifying them is particularly difficult in the first place, let alone then going on to understand what makes them tick. But it's fundamental. If we're really going to make this an available technology for as many kids as possible, we do need to understand about those epithelial stem cells a lot better than we do right now. So, one swallow doth not a summer make, as Shakespeare said, and that is absolutely true. It's all very well we had this wonderful success with this woman in Spain and this short-term success with this kid right now. But we do need to have proper trials of these technologies, albeit designed in interesting ways to allow incremental improvement, but we do need formal trials to see what really works and what doesn't. I think even before that, though, we need to take what we've learned, take some of the biopsy tissues and blood tissues from these patients and take them back into the laboratory again and work with the best possible scientists we can in biomaterials, in proteomics, in genomics, in whatever fields are at all appropriate. Thank you. And if it's my wife, I'm not home, okay? And apply them to improving this for patients in the future. This is what's called reverse translation. Translation is the phenomenon where you take cutting-edge science and turn it into clinical practice. But reverse translation is, if anything, more important. Learning from what we've done and putting it back into the lab so that in the future we can keep refining things, using the best of science and the best of technologies. We also need time too. 2.5 years is probably okay to say that it's worked in our adult patient, but 6 months is certainly not enough time to say it's worked in the kid. I can't tell you now that this is still going to be working in another 6 months' time, let alone in 5 years' time. I can't also tell you that the stem cells that we've been using and manipulating and the growth factors that we squirted into him are not going to induce tumours in years to come, because we have at the back of our mind the potential for that being the case. We don't think so. We've been working with mesenchymal stem cells, and about 10,000 patients have received mesenchymal stem cells as a form of treatment for hematological problems. So worldwide, there has a pretty good safety record. But we don't know. We certainly do need time to follow these patients up. We need numbers and time and reverse translation. But going back to my point, does this get me closer to addressing my dream of replacing this really complex but fundamentally human organ, the larynx? Well, first of all, we need scaffolds, we need cells, we need blood vessels, muscles and nerves, and again, added value. I think by studying something as complex as this, even if we don't achieve my dream, I think we will have got some way down the road to understanding how we can use stem cells and regenerative medicine to address the problems of other innervated organs, muscular organs too. Yeah. Oh, that's a pretty horrible slide, isn't it? They're not that bad, are they? Let's face it. So this is a decellularized larynx. This is what it looks like. It's still got colour in it, so you may think that it's still got cells in it. But actually, if you look at it under the microscope, control tissue here, the nuclei have all gone. What you're left behind here you've certainly got stuff left behind. And there's plenty of things that kind of look like muscle fibres, but we know nuclei, vocal cord, nothing here that looks like cells there. And if you stain this up critically, what this is showing you here is that on this side here, red are those molecules which would be recognised as foreign were you to put them into another person. So this is what we spend all our time in transplantation trying to downregulate. It's the response to the MHC molecules, the things which cause classical transplant rejection. But in our tissues here, there's no red. We've reached the point where our protocols remove those antigens which would make rejection occur. Therefore, we do not need to immunosuppress people, provided we're using their own cells. The tissues do not reject, we think. We still need to follow the patients, of course. We do check our patients, by the way, to see whether they develop antibodies against the donors, and none of them so far have. Now, these scaffolds we initially thought were just building blocks, just scaffolds, really, like the scaffold around a house when you're rebuilding a house. They're there for support, and when they go away and they've done their job, you don't need a scaffold anymore once your house is built. Likewise, once the organ's built, you don't need a scaffold anymore. But we and anybody who's studying this field is starting to realise that it does a lot more than just build things. There are lots of active things going on in there. So we started to do proteomics. We've studied the proteins within our scaffold. If you do proteomics of something with cells in it, you're left with a very complex mixture of things, which bioinformatics would still struggles with, to a degree, I think. You're left with tens of thousands of molecules, maybe even hundreds of thousands of molecules. Happily here, we were left with something like 350 active molecules, which is neat, because it's a nice number. It's a number where you can actually start putting them into groups of molecules that help stem cells go where they're supposed to go, groups of molecules that hinder them, groups of molecules that allow blood vessel growth, and ones that do not, ones that are immunologically active and ones that are not. It's an interesting group of molecules. What we do know is that these biological scaffolds work a damn sight better than anything synthetic. So whatever the mixture is within them, in general, it's a positive thing. If we can work out what those positive things are, we could then put them into synthetic scaffolds, bioengineered scaffolds, and we could have these off the shelf. Because you can tailor the biomechanical properties of biomaterials in a way that you can't necessarily do with biological materials. That is the nirvana. It's bringing the two things together, having the off-the-shelf, engineered, industrial product combined with the benefits of a biological product by understanding it more. And we're really at the very beginnings of understanding what makes biological scaffolds really tick. This is in fact VEGF. It's a molecule highly involved in the development of blood vessels. VEGF on its own doesn't cause terribly useful blood vessel formation, in fact, but in combination with some other things, you get quite nice blood vessels, like this one here in simulated. So synthetic scaffolds will hold the key to the future, and there's a whole host of ways of building synthetic scaffolds, which I'm not going to go into detail. We're actually developing a very nice gel at the moment. It's not a hydrogel, it's a completely new sort of gel from basic chemical principles up. Okay, so what about the internal lining? As I say, the nirvana here is to understand the stem cells of the epithelium, because if we can understand that, we can start to generate the epithelium that the kid didn't have in the first place. And we did develop a protocol which allowed us to grow up epithelial cells for the first patient, and probably what we were doing there, in retrospect, was actually growing up progenitor cells. That is, cells which aren't stem cells, but aren't fully differentiated either. They had little rosettes around them, which suggests that they have some stem-like properties without being stem cells. So we're starting to study whether we can use these progenitor cells, per se, to make better internal coverings. And they develop like that. It would also be very nice to know where all these cells are going in the body. We're squirting them in willy-nilly, and they're just going wherever. We would like to know not only where they're going, but how many cycles of differentiation they're going to, what they turn into when they get there, and do they hang around? Or do they just hang around for a little bit and tell the body's innate cells to do whatever they're going to do? And we simply don't know the answer to these questions. So how do you chase cells in vivo? Well, one potential way of doing this is by using, these are called quantum dots. This is quantum dot technology. This is a chicken leg, so not too scary, I hope. Unless there's vegetarians out there, of course. Yeah. And here we've used quantum dot technology to stain up a couple of different types of molecule. It's a bit, it's a bit showmanship here. But the wonderful thing about quantum dots is it's pretty non-toxic, and we're hoping that we are getting close to being able to actually use this in man and not just animals. Every time a cell divides, if you can stain up different colours of cell, different types of cell with different colours, every time it divides, the amount of colour halves. So you can work out how many cell cycles it's gone through. And if an mesenchymal stem cell turns into a chondrocyte, it'll remain green. It'll have gone green. So you can tell where the cells have gone and what they've turned into. So we are hoping that this is one way of doing that. Blood vessels are a big issue, and the bigger the organs you generate, the more this is going to be a problem. The larynx is fairly complex, bowel even more so. There's really no great solution for long length of bowel loss, or lung loss for that matter. But actually, you can decellularize organs through their blood vessels. And if you start passing blood through these scaffolds again, they develop their own endothelial lining. They will actually pick up circulating pre-blood vessel stem cells, which we all have going around in our circulation. And this is a very positive thing. So we never thought this would work, actually, but we just tried this out in a rat, in fact. So this was native. And when we decellularized it and pumped blood around, it didn't leak. The blood didn't leak out. It actually developed a circulation again. So there's clearly some potential here for decellularizing even quite big organs by using their own blood vessels, A, to decellularize, and B, to revascularize them afterwards. And this is quite a fruitful area of research in the future. Muscles are an issue. How do you do? Well, there are lots of groups working on different types of muscle now, and you may even have seen some of the publicity around people building hearts and things. This is a model for a complex bioreactor in which you can grow up different types of cell. In essence, you can get stem cells to do all sorts of things, not just depending on the types of growth factors that you apply to them, but the environment in which they find themselves. They will actually pick up on biomechanical cues. And so if the biomechanical cue that you're placing on it is stretch and contract, they will tend to form muscle fibres of a certain sort, either slow or fast. If they are like a heart, then they can start to form into cardiac fibres, very crudely, provided other aspects of the environment are correct. So dynamic bioreactors which this is, it's a box in which you can grow cells, but it actually does things, it moves things in and out, can persuade cells to do things that they wouldn't otherwise do. And it's a nice way, in the future, we hope, of building actual muscles. So what about the lungs? Because, after all, I did bring you here under false pretenses, so I might as well talk a bit about lungs. I mean, pulmonary disease is huge. I mean, it causes about 4 million deaths a year in the US. It's one of the commonest causes of death. It's about the fourth highest cause of death in the US, in fact. So it's absolutely immense. And for a lot of these conditions, there are inadequate treatments for people with advanced asthma and so on. Really very inadequate treatments. So there's an awful lot of work going on into studying stem cell technologies for lung disease. And you can do a number of different things. You can either inject things straight into the lungs. You can inhale things. After all, the windpipe goes straight down. You can inhale things. You can implant things. Or you can put things into the circulation that home in on the lungs afterwards. Of all of these routes, however, the most promising is actually direct implantation. Because if you just put stem cells into the body, just willy-nilly again. Sorry if I keep using the word willy. It's a British phrase. What goes so randomly. Okay. 95% of the cells will die before they get to the target organ. Very few of them will hang around for more than a day once they get there. And then even fewer of them will actually do anything constructive. So trials with heart disease, for example, have shown this. And similar things seem to be happening with lung too. There have been some promising results in patients with pulmonary hypertension, but that's primarily a problem of the blood vessels rather than the actual parenchymal tissue, the lung tissue. So really, all the pointers at the moment are pointing towards, as we found, combinations of cells with appropriate scaffolding support, and not cells just on their own. And so, in the early part of this year, Langer's group in Boston had this big hit, where New England researchers create functional lung tissues, the Boston Globe. But this did reach the headlines, and what they did here, so this is a scary part because it's got a mouse in it. That's pretty scary, isn't it? I put it out of focus just in case any ladies wanted to jump on their chairs at this point, but I'm sure it's not going to happen. Oh my God, that was sexist as well. I better go. No. Never mind. I'll gloss over it. So what they did here was they actually did a sequence of experiments building up through primary cell cultures, experiments with scaffolds. They built organotypic models, which is where you take cells and scaffolds and build something that looks a bit like the tissue of interest in the laboratory. And then they actually built something on a pump that actually inflated and deflated and had gas exchange as they pumped around blood. And finally, they did a lung transplant into a mouse and found that they got functional gas exchange for as long as 24 hours, in fact. So there was some problems, and then it ceased to work as well. It's the beginning. But again, here, they were using scaffold and cells in combination to regenerate lung tissue, and it appeared to be functional. So I think there's great promise there too. So I would hope that true regeneration will become possible by stimulating the body's own systems to rebuild, by a fundamental understanding of the stem cells that we're putting into people, and the ones that we're not, the ones that are already there, and stimulating them to do what they're meant to be doing. And so it's also timely that at this point that we look at embryonic stem cells. And I appreciate under previous governments this has been quite an issue here, and in Britain too, to a degree. We're actually doing some embryonic work at University College London on the eye. In fact, we've got a big grant with CERM, in fact, jointly with CERM, the California Institute of Genetic Medicine, where we're using embryonic stem cells to look at macular degeneration, which is the commonest cause of blindness in the elderly. It's an appropriate site because the back of the eye is what's called a privileged site. It's a place where tissues don't reject. So it's a good place to put things which would reject in any other setting. And talking to my colleague who does this work, so I'm going to ask you a question. You shouldn't say that, should you? How many embryos do you think would be needed to generate a treatment for everybody in the world today with retinal degeneration? How many human embryos? Everybody, the whole world's population for retinal degeneration, macular degeneration. Have a guess. Pick a number. Gerhard, you probably know the answer. That's the answer. The answer is you need one embryo. Because the whole point about stem cells is that, particularly embryonics, is they have almost infinite capacity to regenerate. You don't need to keep killing embryos. You only need one to cure everybody with macular degeneration. Anyway, so the barriers are starting to fall. This is actually the first trial of embryonic stem cells in humans, and this is for neurodegenerative disease. And this is Geron, who've been trying to get this permission for a long, long time. I think Geron are from Silicon Valley, near here, but this is going to be in the northwest, I think, northeast. So we wait with bated breath to see what the true impact of embryonic stem cells is going to be. A group in Sweden have used embryonic stem cells from mice and put them into rabbits and regenerated a whole vocal cord, which clearly causes me great excitement because this raises the possibility that perhaps we won't have to do huge operations, that perhaps we will be able to use embryonic stem cells or induced embryonic stem cells to actually regenerate large bits of the tissue that I am particularly interested in the future. And I'm indebted to Christopher Reeve for the next quote. Christopher Reeve was one of the people who did a lot to help CERN get off the ground and also to change the regulation in the US, as you know. Unfortunately, all this has happened rather later, too late to help him, but I think he did give an important stimulus to the field. So many of our dreams at first seem impossible, like the idea of building a larynx, which is a ridiculous concept. Then they start to seem improbable when you've investigated transplantation and that's got a lot of problems and you can't get nerves and muscles to work again. But when you summon the will and you keep studying it, and particularly when you engage with the very best of scientists and technologists to get them interested in the very real problems that you're seeing in the clinic, I think the treatments for these people will become inevitable. These are the people who I'm greatly indebted to, particularly Paolo Macchiarini, who's been my partner on this journey, a great and very brave surgeon. Mark Liddell, who has the stem cell facility that we're using, Alex Sefelian, who generates the biomaterials and bioreactors, Sam James is the pulmonologist I work with. Ian Rees actually works for our regulators, unbelievably. We do actually work with our regulators. It's hard work. Anyway. John Egan is a representative of British industry, who we work with too. Numerous fellows and PhDs who, of course, really do all the work, don't they? They really do all the hard work. We just go and have coffee, and they do the work. And our funders. And I have to say that up until 2 weeks ago, this actually said, and we have had no funding. Because it's true that up until 2 weeks ago, all this work with the child and had no substantial funding whatsoever. We kind of patched together grants to do all this. But happily, the Medical Research Council have now given us £1.5 million to get going on laryngeal replacement. So there we are. I have a dream. We're inching our way forward down this pathway. I think even if we don't get there, I think the spin-offs are going to be huge. And thanks for listening to me. And I'm happy to take any questions, actually. So, being a public lecture, it's supposed to be. So. Yeah, not as many as we'd like is the answer. Realistically, we're getting down to about 4 at the moment. But we have hopes we can do better than that. But certainly, with the ones we've got at our disposal, it's about 4. So. Yeah.
Oh, hey.
I don't quite understand the concept there. No, that's okay. So you're saying that generally, so take for example the context of intrapulmonary injection of stem cells or intracardiac stem cells, that the majority of them die en route or when they get there. But in the laboratory, they have a great capacity to survive. That's essentially what you're saying, I think, isn't it? Well, I think the conditions in the laboratory are extremely favourable compared to putting a stem cell through a piece of plastic and then through a metal needle and then into an airway which is full of bacteria and viruses, and then hoping that somehow this really quite vulnerable cell is actually still going to make it down to where you're trying to get it to. The manipulation required to deliver these things is really not where it should be. And perhaps that's another field that we should be concentrating on, is actually delivering the stem cells better, to make sure that they're more effective and get there in better numbers. Maybe encapsulating them in some way, using polymers and biodegradable materials. Slow-release stem cells. So,
what's the role of respiratory therapists in kind of research that I went through? And what is the leading study of respiratory therapists in this kind of research?
okay, no, that's a very good question. Okay, I'll digress a bit first. I've been known to digress. You probably gathered that, but anyway. When we did the first patient, we did it in Spain, and the pulmonary therapist, we call physiotherapist, who's involved, was from Brazil. And we were doing all this dissection around in the chest, the woman's chest, getting it all clear. And that part of the chest is called the carina, as you know. And I turned to her and said, "This is fantastic, isn't it?" I said, "What you called?" And she said, "Carina." She was actually a pulmonary physiologist. It's not that funny, okay? I laugh. So she actually was called Carina. We were operating on the Carina. But anyway. So thank you, madam. I'm here all week. Anyway, so anyway, okay. It's very early days, and we're just starting to see the first fruits of regenerative medicine creeping into the clinic. So in terms of making these routine therapies, we're certainly looking 10 years, I think, for the first wave. That doesn't mean to say, however, we shouldn't be starting to educate our workforce for the future. And that has to be a multidisciplinary workforce at every level. So not only the laboratory scientists, and there's some fantastic young people going through the master's degree here at the moment, the technologists involved, but also young doctors going to a whole raft of specialties. Engineers, young engineers need to be getting interested in this to make the bioreactors that we're going to need, the chemists to make the polymers, the bioinformaticians who are going to be able to interpret it all for us. So all of that side of things. But we are going to need a clinical workforce as well. And what that clinical workforce is going to look like, I cannot say. But it most certainly will involve paramedical specialties. I think that'll be fundamental. It may be, for instance, that you're going to be the people responsible for appropriately monitoring the function of the organs that we build, and maybe even administering some of the growth factors necessary to keep them functional. So.
And are there any parallel procedures that are similar in the veterinary world?
Okay, two cracking questions there. So the first question was, do we have any difficulty recruiting patients? No, actually. We have the reverse problem. The reverse problem is actually being able to operate on them in the first place. We are able to do these procedures under what's called specials licenses. So we are able to manufacture products on a one-off basis under special regulatory control, provided we have the highest levels of what's called GMP facility, like Gerhard knows. We've got all that and the appropriate licenses in place and appropriate ethical permission. But these are only for one-off cases where there is absolutely no conventional treatment and that the result of not treating would be severe. So you're dealing with desperate patients. The world is full of desperate patients, and they're all writing to us. And I get emails every day with people with every kind of disease saying, can you help us? And for a very small number of desperate people, yes, we can invoke this, but we can't keep invoking this. As soon as you plan to do 10 desperate people, if I went to the MHRA or the FDA and said, I'm planning to do 10 people who are going to die if I don't do them, they immediately say, this is a clinical trial. So it's no longer under special license. So you immediately then have to invoke the whole regulatory process that takes you 2 years if you're lucky. So that's the framework. So yes, of course, we will continue to operate on desperate people when we can and where we can. And that's actually why we're continuing to involve some European countries where the regulations are not quite so tight. Tight enough, but not quite so tight. Sorry. So that's the first. We're not short of recruits. So the second part of your question was the veterinary medicine field. And I think this is fantastic because there are certainly all the diseases that I deal with have parallels in animals. Yorkshire Terriers get airway collapse. Labradors get airway collapse. Racehorses, after orthopaedic problems with their limbs, the commonest thing that limits them is the airway. They get what's called DDSP, dorsal displacement of the soft palate. They get laryngeal paralysis. The inbred racehorses, it's a genetic thing. So yes, of course, we can, I think, use these patients, veterinary patients, as intermediaries to man, I believe. Actually, in the UK, it's more difficult to experiment on animal patients than it is on people. But I don't think it's quite the same here. I know that you are able to do some horse work and stuff here, which is great. So there's great potential there, both using animal models for human disease, but also for treating important veterinary diseases, and then learning from that in a way which will help us with people.
Falling back to the previous question, as an individual with your MD, you also do research. How do you find yourself prepared for the research field that you're going to say MD and PhD? Are you approaching research from a different angle?
No, that's a great question, and it's one that was asked earlier on, and it's one of my favourite questions actually. So, because, to be an academic physician, let alone an academic surgeon, is a very difficult thing. You stand in the middle of a bridge. It's a very wobbly rope bridge, and at one end you have scientists who toughed it out, like all you guys, toughed it out, did it the hard way. So they went to college and they did the degree. They did a PhD on no funds whatsoever and ate McDonald's the whole time. They then have gaps between their postdocs, and eventually they might build a research group, and eventually, if they're lucky, they'll get the grants to sustain something. So they've done all that, and they've managed to achieve great things in that way. And I've never had to do that. I've had it easy because I've had a medical degree, and I've dipped in and out of medicine and science as I felt like. And I get around talking about science as though I know something about it, which I don't. And so the scientists view me with some suspicion. And at the other end of the bridge, you have your full-time surgeons who look at this guy and they think, what the hell's he doing over there, messing around with scientists? You know, surely he should be spending all his time. If he's not spending all his time in the operating theatre, like one of the guys at UC Davis came and said, I've spent 10 out of the last 11 days operating. Oh, tremendous. That's great. I'm glad I'm not your next patient. But if you're not spent all that time there, then you can't possibly be a proper surgeon. So you have this dichotomy. Plus, on the other hand, you have less time to devote to writing your grants and doing your research than even there's surgeons, even as a physician scientist, let alone a full-time scientist. And that's a very difficult place to be. And, okay, I get well paid, but you get much less well paid than your surgical full-time counterparts. And so you have pressures at home and all that. So it is an interesting place to be, but it's a fantastically exciting place to be, and it's an essential place to be. And any MD who's interested in doing research, I would thoroughly encourage it. Because people who go to medical school and veterinary school are the brightest in many ways of their cohorts. And why should all of that be stripped out of them to do some of the very mundane jobs like castrating dogs or taking tonsils out? You know, they're incredibly mundane. And I think those people who choose the more scientific path to walk hand in hand with the scientists are going to have a much more fulfilled time. Certainly, I certainly have.
What's the potential for using fetal tissue stem cells in your type of research and work? And in the UK specifically, what are the limitations?
Okay. The answer to the first is I don't know, but as I say, there have recently been some very promising results for regenerating whole vocal cords. So that's muscle, lamina propria, nerves, mucous membrane, and therefore allowing people with very hoarse voices, post-cancer usually, to talk again. And it's difficult at the moment to visualize how you could do that using the scaffold cell technique, which is really very crude and typically surgical thing to do. So yes, I do think there's potential, and I'm very keen to explore that boundary a little bit further. Even though presently, in my part of the body, you'd have to immunosuppress the patients. Of course, there are now inducible pluripotent stem cells too, and we're all hoping and praying that they will fill the gap. I'm not sure they're living up immediately to the promise that they initially had, but if they do, then that would be an obvious place to go. Do you all know what inducible pluripotent stem cells are? Essentially, you can take a skin cell, and by applying a certain combination of growth factors, you can make an adult, mature, differentiated cell go backwards and start to behave like a stem cell, and have many of the properties of a classical stem cell. So it's a very interesting technology. So maybe, yeah, absolutely, we should have some potential there. Okay, the other question is about regulation, and it's really very tough indeed. We decided that not only were we going to have a HTA regulating the tissues that we're using, an MHRA, which is really used to dealing with drug control. They're not used to dealing with, anything as complex as this. But we would superimpose on top of that GTAC, which is our gene therapy administration program too. So I have another slide which shows you the pathway, and it's just ludicrous. It really is. So the minute you start, sorry, there's another one for embryonics. I beg your pardon. The embryonic regulation pathway. I beg your pardon. So there's a separate one for gene therapy too, but there is an embryonic body too. So it just becomes ludicrous. Does that mean we shouldn't embark upon it? No, I don't think so, and I think I would very, very keen to tentatively start exploring that field. But we're achieving so much with what we're using at the moment. That I think it's beholden on us to learn as much as we can about the present technology. So that's mainly where my efforts are going. Some dogs need castrating, I think. No. Okay. Well, yeah, no, please. Yeah. Oh, right, no, I did my fellowship in Brisbane, in Queensland, which is kind of, it's the, I don't know what the equivalent would be. Is anybody from Alabama here? No, so I won't be rude about Alabama, I'm just making the analogy, that's all. And it was, at that time in the early 90s, it was still an extremely conservative state, it has to be said. But they drained the whole South Pacific, so there was an enormous pool of patients to operate on, and they kind of threw them at the British Fellows, so you really learned to cut. Productively, I hope. I hope some of the patients are cured. Yeah, yeah, please. No, it's not. It's off. Oh, I forgot to announce which video not to use, by the way. I'm sorry. It'd be nice if you could cut it, the third one, but, well, so, no, that's not published yet, no. But I think there are other groups doing similar things. We're also, we've put a big grant in to look at angiogenesis as well. But as I was alluding to when I showed you the molecule of VEGF, it needs to be very controlled. You don't want willy-nilly growth. What's the third willy-nilly? That's three. So I've thrown 3 willies at you already. That's an extremely rude thing to do, isn't it? But, so VEGF induces a kind of random generation of capillaries, essentially. What we really want is arteriogenesis. An arteriole is 1,000 times more efficient at delivering oxygen and delivering oxygen anyway, and nutrients. So and there are certain sequences of growth factors which are known to do that, and we'd very much like to explore that sequence of growth factors in our scaffolds.
Is there any research other than the stuff from Boston in regenerating the current kind of long?
Oh, absolutely. No, there is. In Japan particularly, there's some groups there. And they've used collagen scaffold. This was decellularized tissue, but they've used just pure collagen sponge. And collagen sponge is incredibly safe and biodegradable and disappears after a while. They haven't had quite such spectacular results, but they've been trying to regenerate bigger bits of tissue. So, yeah, it's not replicated, but similar work is promising.